Hello guys, this is the second lesson in rotational motion. Write down our first topic, rotational inertia. Right. So Abute, in linear motion, I think you remember inertia. Inertia means the tendency to change the state of motion, right? So in linear motion, that is depending only upon mass of the object, right? So when we come to rotational motion, that rotational inertia, right? So what is rotational inertia? That is the tendency to change of rotational motion, right? So that depends upon two things, right? One is mass of the object as same as in linear motion, right? But there is another one, right? So we can do a small experiment to find that. Okay, first we write down the tendency to change state of rotational motion is called rotational inertia. Next line. In linear motion, inertia depends only upon mass of the object. But in rotational motion, rotational inertia depends upon mass of the object and also upon another quantity. To find that, consider following small experiment. Right. So Bude, this is a pencil. You can take your pencil, right? So first we rotate that about x-axis, right? Law inertia, you can observe that. So when we rotate same pencil, we didn't change the mass of the object, right? But you can see inertia is high, difficult to rotate, right? When we change the axis into y, right? So mass is same, right? So distribution of mass about the axis, that is changed, right? Now about x-axis, you can see this is the distribution limit, right? But when we consider y-axis, you can see that distribution area is large, right? So therefore we can say that second quantity, what is that? That is mass distribution, right? Okay, write down, first copy down this diagram, after that write down, when we rotate the pencil about two axes, it is difficult to rotate about y-axis. It is difficult to rotate about y-axis than x-axis. The reason is the mass remains, while the mass remains same, distribution of mass increases about y-axis. Therefore followings are the quantities that rotational inertia depends. Okay, then put a number 1, write down mass of the object, second one distribution of mass, about the axis. Right, write this and highlight. Okay, so to represent that rotational inertia, we use a quantity we call that moment of inertia. Right, notation is I. Write down. To represent rotational inertia, we use moment of inertia of the object. Right. So then next topic, write down moment of inertia. Okay, so first we discuss about moment of inertia of a point mass, a small mass at simple r perpendicular distance from the axis, right? Okay, write down. We can define moment of inertia at simple r perpendicular distance moment of inertia at simple r perpendicular distance from axis of rotation of the object, axis of rotation we consider, comma for a point mass simple m, as follows, right? Okay, highlight that for a point mass simple m, and perpendicular distance simple r, then from considering rotational axis, right? Okay, so I is equal to mr squared, right? This is the equation. Then m is equal to that unit of m, that is kilograms, right? So distance we can measure using meters, therefore meter squared, right? So SI unit of I, that is kilograms meter square, right? Okay, then write down moment of inertia is a scalar quantity, and SI unit is kilogram meter square. Okay, write down this question. What is moment of inertia? What is moment of inertia of point mass 50 grams? Point mass 50 grams located at 10 centimeter perpendicular distance from the axis, from the considering axis. Right, a small question. You can use the equation I is equal to m r squared, then 50 we can convert that into kilograms, 10 to the power minus 3, then r, that is in meters, 0.1 square, right? Then 15 to 10 to the power minus 5, that means 5.0 into 10 to the power minus 4 kilograms meter square. Right. Then we write down next subheading. Now we discuss about a single moment of inertia about single mass. Then we discuss about system of masses, right? Okay, then write down moment of inertia subheading.
Hello, Uncle.
Of a system of masses. Right, this is the subheading. Right, so about axis through point O. Now you can see there we have several masses. So we can write I is equal to, I total is equal to addition of all these, right, moment of inertia. That means I equals sigma m r squared. For this example we can write I total is equal to m1 r1 squared plus m2 r2 squared, m3 r3 squared plus m4 r4 squared likewise, right? Okay, copy down this. Right, so this is the next question, right? So this is the question. Assume distance are in meters, right? So this y and x. Now this is a Cartesian plane, right? So masses are located like in this diagram, right? So so the distances we take them, we assume that are in meters. So we need to find moment of inertia about y-axis and x-axis, right? Okay, right, first copy down this question. Then right, about y-axis. Okay. Right, about y-axis, these are the distances. 2 meters, right, then 3 kilograms, that is again 3 meters, right, then 6 kilogram there, that is 2 meters, right? Now when we mark distances, we don't take that minus sign, right? Distance is a now perpendicular distance, that is a scalar quantity, no signs, right? Then 4 kilograms from the axis, that distance again 1 meters, right? So Abhuday, we consider only these masses, right? You can see we are not having moment of inertia about y-axis by these masses, right? What is the reason for that? So you can see they are located on the axis, right? So this is the axis, rotational axis on the axis, right? So when we consider on the axis, right, I is equal to mr squared, right? If the object is on the axis, what is the value of r? That is 0, right? Then I becomes 0, right? Therefore, when the object is on the axis, on that considering axis, we don't have moment of inertia by that object, right? Okay, write down. First write down. If considering mass, if considering mass is located on rotational axis, is located on rotational axis, moment of inertia of that object is zero because r equals 0, then I equals mr squared, then I equals m into 0 squared, that is 0, right? So they highlight that sentence. When the mass is located on the axis, I becomes 0, right? Okay, then we consider this one, Roman number 1, Iy equals, right, 2 perpendicular distance, now mr squared we write, 2 perpendicular distance also 2 square, then second mass 3 perpendicular distance also 3 square, right, plus this is the third one, mass 6 perpendicular distance 2 meters 2 square, and 4 into perpendicular distance 1 square, right? Okay, then you can find the value. Right, so when we calculate the value Iy, this is the value for Iy, right? So similarly you can find moment of inertia about x-axis, right? First we mark perpendicular distances from x-axis, right? For this one that is 3 meters, and for this one that is 2 meters, right? Here that is 1 meters, and for this one that is 3 meters. Okay, then we can write Ix equals, right, look at here now, 1 kilogram distance 3 square, right? Okay, so this is the axis for the rotation axis, plus here 5 into perpendicular distance 1 square, plus, and here what we have 2 into perpendicular distance 2 square, right, and here 4 into perpendicular distance 3 square, right? Then you need to add them. So in this situation also you can see these masses 3 kilogram, 7 kilogram and 6 kilogram, these masses are located on the axis, therefore we don't have moment of inertia by that objects, right? Okay, find the value, right? So this is the answer for moment of inertia about x-axis. Okay, so the moment of inertia of different objects, right? Now when we find the moment of inertia, we use that equation I equals sigma mr squared. Now when we use that equation to find moment of inertia of a different object, right, we need to use integration in mathematics, right? Eva biolama නැතිඳ, right? අපි මෙහෙම objects ටිකක් තියෙනවා, ඒ ටික ගැන දැනගන්න ඕනේ moment of inertia equations, right? Okay, so ඔක්කොම ඔයාලා මතක තියාගන්න ඕනේ. I have put there star මේ stars දාලා තියෙන දෙක නම් විභාගෙට දෙන්නේ නැහැ. අනිත් ඒවා නම් ගොඩක් වෙලාවට paper එකේ ඔයාලට දෙනවා. Right? Okay. So the first one, uniform thin disc pulley or a solid cylinder. Right? Okay. For that, I is equal to half mr square. Right? And here this is a uniform thin hoop, right? So for that one, that is I equals mr square, right? එතකොට මංගල බුදු වාල වලලු ඕන එකට දාන්න පුළුවන් මාල් නැහැ. බුදු වලලු ඕන එකට දාන්න පුළුවන් second equation එක I equals mr square, right? So Pute, you need to have an idea how we change that value of I, right? When we change the distribution of mass, right? Now compare this first one and the second one, right? Same mass is there, capital M, same radius is there, right? Now when we making that second one, what happens to distribution of mass, right? මේ මැද තියෙන ටික කපලා, right? උණු කරලා වටේට වක් කරන්න වෙනවානේ. Then what happens to distribution of mass? That increases, right? So distribution of mass increases, therefore you can see I value for second one for hoop that is greater than that of disc, right? Okay. මේ වගේ දෙගුණයක් තමයි මෙයාගේ. ඒතකොට මෙයාගේ mass distribution එක වැඩි වෙච්ච හින්දා තමයි වැඩි වෙලා තියෙන්නේ I ගේ value එක, right? Okay. Right, then we consider a uniform rod length L. Right, now we change the axis, right? When we consider an axis through the center of the rod, right? This is the value of I, right? And this is when we consider axis through a point of the corner, right? So you can see that I value is greater for this situation. What is the reason? When we consider mass distribution of mass about the axis for this one, so we need to consider farthest point, right? Farthest point there, right? That distribution of mass is high, therefore that value I is lower than greater than previous one, right? Okay. Right, after that, solid sphere and hollow sphere, they have same masses, right? Now when we consider solid sphere, this is the rotational axis that is going through the center of the sphere, right? So there we have masses closer to the axis, therefore I value is lower than that hollow sphere, right? මේකේ I එක මෙයා දැන් මෙන්න මේ mass එක තියෙනවනේ මේ axis එකට ළඟින්, ඒකින්ද මේකේ I ගේ value එක අඩුයි මෙයාට වඩා. මෙයාගේ ඔක්කොම තියෙන මේකේ thin shell එක, right? So all the masses are located on shell, right? So the mass distribution වැඩි, therefore value of I also large, right? මේකේ එතකොට නිකන් solid එකක්, right? ඒ කියන්නේ solid එකක් මේකේ ඇතුලේ මුකුත් නැහැ. අපි කියන්නේ අලියා ගිලපු දියුල් ගෙඩිය වගේ, right? ඒකේ ඇතුලේ මුකුත් නැහැ, shell එක විතරයි තියෙන්නේ, right? Okay, copy down this also. So Pute, now that quantity I is related to mass in linear motion, right? අපි හැම වෙලෙම අර මේ දෙන්නගේ relationship එකක් බලනවනේ. එතකොට mass වලට තමයි මෙයා related. So highlight that also. So we can replace mass in linear motion with I, right? Okay, then write down next subheading, right? So next topic is torque. Right, now actually torque means that is another name for moment of a force, right? So you know definition for moment of a force. If this is the force, line of action of force, this is the perpendicular distance, right? Then we can write tau is equal to, right, that is having rotation direction, tau is equal to F into D, right? moment එකම තමයි. right කලින් අපි ඉරගෙන තියෙන moment ම තමයි rotation motion lesson එකේදී අපි මෙයාට කියන්නේ torque කියලා. right so unit we can write Newton meters, right? That is the unit of torque, right? Okay, write down. First copy down this. Okay, write down torque is a vector quantity. Torque is a vector quantity that has a rotational direction. That has a rotational direction. Within brackets, write down clockwise or anti-clockwise. Clockwise or anti-clockwise. Right. So this is also a new quantity. Then that torque is related to F in linear motion. Right. So highlight that also. Okay, so we can use torque, right? Torque to have two equations related to Newton's law expressions, right? Newton's second law, I think you remember we discussed two equations, right? So first one is F into D. Sorry, F into T equals mv minus u, right? So we can replace this with rotational motion quantities. Tau is there, right? T is same. Then we can write I for m and final velocity omega minus omega naught, right? So this is the equation number 1. Right, and also we know that very useful equation we used F equals ma. Using that for rotation motion we can write here tau equals I into alpha. Right, this is second equation. Right, so ගණන් හදද්දී ඔයාලට ලේසි මෙහෙම මතක තියාගත්තොත් tau වලට දැන් equations දෙකක් තියෙනවානේ, right? tau වලට, right? First one F into D and second one I into alpha, right? Okay, so copy down this. Right, so this is the example. Now here we need to find moment of inertia, right? We can use, now this is a disk, therefore we can use half mr square, right? Then this is the answer. So we need to find torque also. For that we can use tau equals I alpha, right? Here this is the equation I have used. Tau equals tau equals F into D, right? Force into perpendicular distance, right? So 2 and 0.1 we have converted centimeters into meters, right? So this is the value for tau. After that we need to find alpha. So we can use tau equals I alpha. So here now easy to simplify. If we multiply both numerator and denominator by 2, right? Because denominator value becomes a factor of 10, right? Then මේ වගේ අපි කරනවා නේ සාමාන්‍ය simplify කරද්දී එහෙම ලේසි ක්‍රම වලට හැම වෙලෙම පුරුදු වෙන්න, right? Then here 0.4, here we have 10 into 10 to the power minus 4 means 10 to the power minus 3, right? So 4 into 10 to the power 3. So this is the value for alpha, right? Okay, right. So after that we need to find angular velocity after 1 minute, right? Then right, initially at rest omega naught equals 0, Then alpha we have calculated 4 into 10 to the power 3, right? So after 1 minute means t is equal to 60 seconds, right? So we need to find omega, right? Okay, u තියෙනවා a තියෙනවා t තියෙනවා v find out v equals u plus at. That means omega equals omega naught plus alpha t, right? Then 0 plus alpha 4 into 10 to the power 3 into time taken 1 minute, that means 60, right? Okay, so we can multiply this, right? Here we have 24 into 10 to the power 4 radians per second. This is the answer, right? Okay, then right, in linear motion Pute, we discussed that work done by a force. Likewise in rotational motion work is done by a torque, right? Now consider this is a wheel, right? So a torque is given, external torque, right? Then think that rotation of that disk is theta, right? So we know equation for work done in linear motion. I think you remember that. That is W equals F into D, right? Then we can replace that quantities using rotational motion quantities, right? So W is equal to, instead of F we can write tau, right? Instead of D what we can write, that is theta, you know that, right? So this is the equation for work done in rotational motion, right? Okay, copy down this also. So here also, now this is also a type of energy, therefore this is measured in joules, right? Okay, copy down. Right, then write down next line. We can derive an equation for rate of doing work, comma, power within brackets P, as follows, right? So this is the equation. So we can divide both sides by time, right? So work or energy divided by time, right? Then we have power there, right? So power is equal to tau into theta divided by T. So this is the equation for power, right? I think you remember the unit, right? To measure power, that is watts, right? Okay, copy down this also. Right, so they copy down this question. Right, here we are giving a tangential force to that disk. So we can find torque. Torque is equal to force 4 into meters 0.05 centimeters, right? Then 0.2 Newton meters. This is the torque, right? Then Roman number 2, work done by torque when rotating 2 revolutions, right? So W is equal to tau into theta. So we can write tau 0.2. So theta here 2 revolutions, right? Then that is 2 phi into 2, right? So here take phi equals 3, right? Then we can write 3 there. Okay, so 0.4 into 3, 1.2 Right, for this one we can write 3. Here we have for 8, 0.8, then 2.4, right? That is the value for work done, right? Then today we need to find power, right? So that work is done within that time duration, 1 minute and 40 seconds, right? So power is equal to W over T. 2.4 should be divided by 100 seconds, right? So 2.4 into 10 to the power minus 2 watts. Right, copy down. Okay, then rotational kinetic energy. Now we take this type of an object. So it is having angular velocity omega and moment of inertia I. Right. So this is also similar to linear motion, right? So we know equation for kinetic energy in linear motion, that is half mv square, right? So we can replace these quantities with rotational motion. So here rotational kinetic energy, right? Then right, so half into, instead of m what we can write I, and instead of v what we can write omega, right? So this is the equation for rotational kinetic energy, right? So this one also measured in joules. Any energy, any work done, we measure with joules, right? Okay, copy down.